Hello! We introduced the core last time, which are outcomes that are stable. Such an outcome has the property that, for any coalition C, the payouts received by the members of C is at least the value of the coalition. Now, a cooperative game may have outcomes in the core, but some don't. And the question is, when do games have non-empty cores? And is it possible to find them? In this lecture, we will focus on superadditive games, and this has relations to general cooperative games that we will see in the next lecture. Our goal here is to determine when a superadditive game has a non-empty core. Recall that a game is superadditive if V of S plus V of T is at most V of S union T for any disjoint S and T. This means that forming larger coalitions gives you more value. So ideally, we should be forming the grand coalition. Now, it is still possible that an outcome in the core does not form a grand coalition, and as an exercise, try to find one. But we claim that we can narrow the search down so that we only need to consider outcomes that form the grand coalition. And here is our result. Let NV be a superadditive game. If pi x is in the core, then nx is in the core. This means that if there is something in the core, I can replace the coalition structure with the grand coalition, and it will still be in the core. For our proof, we need to prove two things. The core conditions hold, and nx is a valid outcome. Since pi x is in the core, x of c is at least v of c for all coalitions C. And this still holds for nx, because x has not changed. To show that nx is a valid outcome, we need to verify that x of n is at most v of n. Now x of n is equal to the sum of x of c over all c in pi, and that is because pi is a partition of n. This is less than or equal to the sum of v of c over all c in pi, because pi x is a valid outcome. And this is less than or equal to v of n. And this is where we finally use the superadditivity of the game. And that completes the proof. So, to determine if a superadditive game has a non-empty core, we only need to look at the grand coalition and find possible x's that satisfy the core conditions. For example, let's go back to the unanimity game. Recall that this is a game where the value of s is 1 if s is n, and it is 0 otherwise. It is easy to check that this is a superadditive game. To determine if the core is non-empty, we only need to consider outcomes of the form nx. Now x satisfies the sum of the xi's is equal to 1. That is because a previous proposition tells us that such an outcome is efficient for the coalition structure. And for any subset S, the sum of the xi's is at least 0, and this is from the conditions of being in the core. So any x that satisfies these conditions will be in the core with the grand coalition. For example, we could set xi to be 1 over n for all I, or we could set x1 to be 1 and xi to be 0 otherwise. We now move on to the task of characterizing the superadditive games that have non-empty cores. We will do this in several steps. Now, you may have noticed that we have created a lot of linear inequalities when trying to solve for the core. We will now formalize this process. Suppose we have a superadditive game and we are given an outcome that is nx. So what must x satisfy in order to be in the core? We claim that x must be in this set, which is script C, and that is all the vectors x in Rn that satisfies xn is equal to v of n, which is from the efficiency property, and x of c is at least v of c for all subsets c of n, and that is from the definition of the core. In the example of the ice cream game, script C looks like this, and you can verify these inequalities from the table. Script C is the intersection of hash bases, so it is a polyhedron. And we get this mini result here. MV has a non-empty core if and only if script C is non-empty. And we can solve the problem of is script C non-empty using a linear program. We let P be the following linear program. We minimize x of n subject to x of c is at least v of c for all c a subset of n. We can write down the linear program for our ice cream game here. Now let's explain how solving this linear program solves the problem of is script C non-empty. First, we see that P is feasible. Just take any large values of x. Also, the objective function x of n is at least v of n. That is because this is part of the constraint. So P is bounded. Using the fundamental theorem of linear programming, this implies that P has an optimal solution. So when we solve for P and if we find the optimal value to be v of n, then we have optimal solution x with x of n is equal to v of n, and x of c is at least v of c for all c a subset of n. So then x is in script C. So we can conclude from this that NV has a non-empty core if and only if P has optimal value v of n. Now I know what you're thinking. You desperately want to take the dual of this linear program. So try and see if you can take the dual of this linear program. Each constraint corresponds to a dual variable. There is one constraint for each subset C of n, so we have dual variables yc for each subset C of n. The objective function is the dot product of the dual variables and the right-hand side of the constraint. So it is maximize the sum over all C a subset of n, yc times v of c. There is one dual constraint for each of the primal variables. So for each I in n, we have a constraint in the dual. For each I, we look at which constraints in the primal contains xi. And these are precisely the sets C where I is in C. And the coefficient is 1 in each case. In the objective function, the coefficient of xi is 1, and xi is a free variable. So the constraint is the sum over all C a subset of n and I is belonging to C, yc is equal to 1. Since the primal has inequality constraints, y is at least 0. And that is the dual. In the ice cream game, we have 7 dual variables, ya, yb, yc, all the way down to yabc. And the dual linear program looks like this. Using strong duality, P has optimal value v of n if and only if D has optimal value v of n. And this is if and only if the objective function, the sum of ycvc, is less than or equal to v of n for all feasible solutions y. As a subtle point, figure out is it possible that this sum is strictly less than v of n for all possible y. Our problem of figuring out if NV has a non-empty core comes down to verifying that this inequality holds for all feasible y. But what is the meaning of this? We first look at the meaning of a feasible solution. a vector y satisfying the sum of C subset of n for all I belongs to C of yc is equal to 1 for all I. Let's look at some examples of such feasible solutions. We could have yab is equal to yc is equal to 1. To check that this is feasible, we just have to verify that the sum of all the y's containing A is 1, and so is B and C. Or we could have y of ABC is equal to 1 as another feasible solution. Or, more interestingly, we could have yab equals to ybc equals to yac is equal to 1/2. The sum of all the y values containing A would be yab plus yac, which is 1/2 plus 1/2, which is equal to 1. And similar for B and C. So this is feasible. So what does that mean? For the first two feasible solutions, they correspond to coalition structures, or partitions of N. The first one corresponds to partition of AB and then C, and the second one is the grand coalition ABC. More generally, Y could represent any fractional partition, like the third case here. The meaning of this here is A works for the coalition AB half the time and works for the coalition AC half the time. So it is a total of 1 for A, and similar for B and C. So a feasible solution Y is a generalized coalition structure. YC represents the fraction of time each member will contribute to C, with a total time of 1 from each player. Any such feasible Y is called a balancing weight. So that is the interpretation of any feasible solution Y. We now look at the objective function and try to interpret the inequality sum over C subset of n yc vc is less than or equal to v of n. Let's look at the example of the first feasible solution from above. This translates into yab times v of ab plus yc times v of c is less than or equal to 2. And this simplifies down to v of ab plus v of c is at most 2. Now the left-hand side represents the value of the coalition structure, that is AB and then C, and the right-hand side represents the value of the grand coalition N. And the left-hand side is less than or equal to the right-hand side. Does that remind you of anything from before? It might remind you of a proposition that says that the value of the coalition in the core has to be the maximum possible. That is, we are maximizing social welfare. The inequality we have here is then an extension of this to all the fractional partitions. So the sum of yc v of c is the total value of the fractional partition represented by y. The inequality we have here means that the value of the grand coalition is maximum over the values of any fractional partition, and this generalizes our proposition. Now a game that satisfies this inequality for all balancing weights y is called a balanced game. And we have derived a major theorem in cooperative game theory, which is a characterization of all superadditive games that have non-empty cores. This is called the Bondariva-Shapley theorem. A superadditive cooperative game has a non-empty core if and only if it is balanced. We will note that this theorem is difficult to apply. There are too many things to check, but it is a nice characterization from the theoretical point of view. Now this is a characterization for superadditive games. What about general cooperative games? We will discuss this in the next lecture.